Hello, everyone. Welcome to the preview of Icons 2026. This is a preview of Lecture 2 on Advanced Residue Amplifier Design for Pipeline ADCs. I'm Seung-Tak Ryu from KAIST. In this lecture, we will focus mostly on dynamic amplifier-based residue amplifier implementation. Well, pipeline ADCs are very popular for high resolution and high speed conversion. And we know the residue amplifiers work as a crucial role in that structure. So here, ideal 1.5 B per stage residue amplifiers, the transfer curve is shown. For, for the determined MSBs, the residue amplifier will generate residue, the amplified residue like this, and then backend ADC will further conversion like this. This is the ideal operation. But if we have insufficient residue amplifier gain, for example, as illustrated here, then when we have MSB code changes, we have missing LSBs here, which will give us abrupt code change. So the transfer curve will be nonlinear. So for our target specification, target linearity, there must be some design guideline for the residue amplifier accuracy. So if we see the circuit, the residue amplifier circuit, and if you assume the amplifier is well compensated so that it works as a single port system, when the amplification phase begins, then the residue amplifier will settle exponentially. And if we have a sufficient time for amplification, then the settling error will be just limited by the loop bandwidth, loop gain. And if we have insufficient settling time, then the settling error will be defined, mostly limited by the amplifier's time constant, which is inverse of the loop bandwidth. And in order not to have missing LSBs, so this error should be smaller than the 1 LSB step size of backend ADC. That gives us design criteria for any given specification, right? So when we have bandwidth limited settling error, then we from this knowledge, we can extract the bandwidth. So in the course, we will review a little bit more about this one. And for amplifier design, well, traditionally, we utilized operational amplifier. Well-established structure and lots of topologies are there, but the problem with it is a steady current based operation. And for high performance, we need to burn lots of power. And because of constant bias current and the Miller capacitor, we are likely to be limited by slew. But these days, dynamic amplifiers are popular for its low power advantage. So ring amplifier and floating inverter amplifiers are shown here. As you see here, the ring amplifier is inverter-based structure. Also, floating inverter amplifier is the differential differential inverter amplifier supplied by reservoir capacitor. So their operation is mostly dynamic, so good for low power implementation. Ring amplifier, its dynamic operation depends on the dead zone setting, and floating inverter amplifiers dynamic operation is implemented by the self-quenching characteristic. Okay, and different from operation amplifier, we set typically ring amplifiers dominant port at the output node, and also floating inverter amplifier is similar. And the last stage, it drives the load with class AB control without bias current limitation. Its slew characteristic is very excellent. The floating inverter amplifier's case is similar. So at the beginning, fully charged the reservoir capacitor will drive the load with the set VGS here. Different from the operation amplifiers, we are not so uh, it is not so easy to get high gain from internal nodes because these need to provide wide bandwidth. So the design criteria, design methodology will be pretty different from the operation amplifier when we design the ring amplifier and floating inverter amplifier. So in the course, we will discuss stage by stage or step by step design methodology for dominant pole setting here and for also a target slew rate. The upper stage will be designed, and non-dominant poles will be determined with a target gain. And well, because they are dynamic amplifiers, but still we need to test their stability for a given certain time, right? So we will discuss test bench for AC stability for a given time. And because they are pseudo differential circuits, a common mode feedback implementation will be an issue. Well, even though floating inverter amplifiers theoretically it doesn't require common mode feedback, but when the parasitic is concerned, then we need common mode feedback. And we will discuss more about these, like a transient simulation and the noise considerations. So this one shows one example of ring amplifier. So this is the first stage, the second stage, fully differential, right? Third stage. And for proper operation, proper biocircuit should be designed. And for fully differential implementation, we need to design common mode feedback as well. Desirably, switch capacitor circuit for low power implementation. With more than three stages, we need to make the common mode feedback stable. So we can add some local common mode feedback as well. Once we design dynamic amplifier like this, then we can run transient simulation by implementing it in raised amplifier configuration. So here compares two residue amplifiers transient response. One with a two-stage operation amplifier, another with a ring amplifier. As you see here, the ring amplifier has higher slew rate, which different from the amplifier. Op-amp based residue amplifier design. So in the course, we will implement the dynamic amplifier based residue amplifier, and then we will check AC simulation, and also we will learn transient simulation, and we will see this kind of behavior. Okay, so hope we can discuss more about the dynamic amplifiers in May. So yeah, hope we can meet there. Thank you.